there's a way to make an entrance.
This is my destiny.
It was now a conspiracy of witches.
Download Veely today.
Extinct. The very word is chilling. It means that a species no longer survives in this world. Already there have been 5 great extinction events in the history of our planet. What if the next species to be obliterated were us? We pay scant regard to the planet-sized mechanism churning below our feet and over our heads. We are, after all, the apex species of planet Earth. We flourish, we consume, and we drive the natural world to oblivion. Only when a dramatic event strikes, earthquake, eruption, tsunami, are we reminded of nature's awesome force. Sometimes, for reasons we shall explore, Earth and the species on it come to blows. Are we next to be knocked out? History teaches us only what to expect. We have at least those 5 catastrophic planetary events to learn from, if we are to avoid a human calamity.
The Earth has suffered 5 great mass extinction events, and this has been since the last 500 million years. These have been dubbed the Great Five, or the Big Five.
The first recognized one is the End Ordovician mass extinction, which brought to an abrupt halt sort of a big diversification event where lots of new groups evolved.
It's not known whether there were really any plants at all on land before that.
And it's now thought that the main reason this happened was a massive ice age, very brief, probably less than 1 million years in length. For comparison, our current ice age that we're in has lasted for at least 2.5, possibly 5 million years. So this was very brief and very sharp, so sea levels fell very quickly, lots of environments were lost, and then it ended abruptly again. Sea levels rose again, so it caused more disruption.
Certainly after that, we've got evidence, hard evidence of pollen from the land, and even some insects and things showing that life had moved out onto the land during the late Ordovician and into the Silurian. But after that, soon after that, they actually started to evolve into large trees during the Devonian, late Silurian and into the Devonian. And so there are what we see today known as lycopods, or club mosses, little moss-like things that live near water still. And today they're quite small, but they were able to grow into these large trees, the first large trees and first forests. And these forests actually altered, we have evidence they altered the carbon cycle. Because these large trees were able to grow across the empty landscapes, their roots dug down into the soils and they caused extreme erosion. And so the soils were actually then washed away into the oceans, and this changed the whole carbon cycle.
The next one was the late Devonian mass extinction. In that case, it appears that lots of the ocean just suffocated, basically. There were things going on that caused the ocean to lose a lot of its oxygen. Possibly newly evolved land plants caused a lot more erosion by digging in their roots and causing nutrients to run off, causing algal blooms, which sucked oxygen out as they decayed.
And a lot of evidence does point towards these significant changes on the land and to the carbon cycle as being one of the primary drivers of the mass extinction.
And so the ocean floors became sort of dead zones, and there were several pulses. It wasn't just one individual event. So this spread out over millions of years, quite different to the previous one, as I mentioned.
It's hard for people to really imagine this, but there are more types of animals in the past than there are today. So even right before, before the dinosaurs at this point in time, we're talking about the Permian, right before the biggest extinction event ever, the Permian-Triassic mass extinction, there were huge diversities of different types of animals and really complex so-called ecological tiering as well, arguably as complex as today. And people don't realize that there were just so many more different types of animals. And with each subsequent extinction, we keep losing body plans. So as today, if we're on the verge of another great extinction, we can actually show in the past that this has happened, where we lose all these body plans. And there are some organisms which are really rare today, and they're on the brink of extinction. And we can actually see we're going to lose major body plans again unless they're conserved. But we can actually look and learn a lot from the fossil record to show what actually can happen after a mass extinction and how the world changes or can change.
The largest mass extinction event ever to occur almost entirely wiped life from Earth.
The greatest extinction event to ever strike the Earth occurred about 252 million years ago. This is called the Great Dying, but it's at the Permian-Triassic mass extinction boundary. So at this point in time, as far as we know from all of the fossil studies that have been done in terms of all the geologic sections around the planet, on land and in the sea, we know that the extinction magnitude was on a scale that we just really can't imagine, at about 95% of all life on the planet becoming extinct.
It was the only mass extinction that affected insects, as far as we know. The other ones seem to not affect insects as much. And it's thought to probably be caused by a whole combination of events that caused a perfect storm of bad environments. So you had things like a major greenhouse event spike, place warmed by up to 10 degrees very quickly, possibly multiple times. There's even the thought that a new type of bacterium evolved that was able to decompose carbon on the seafloor and turn it into methane, which is a powerful greenhouse gas.
So this affected the carbon dioxide in the atmosphere, and there's also a lot of acids and toxins released into the atmosphere. So this would have really affected the life on the land, and particularly the plants themselves. So these huge forests were actually wiped out at this time.
And probably a lot of hydrogen sulfide came out of the oceans because they were stagnating, and hydrogen sulfide is quite a toxic gas, and it caused a lot of things to maybe die out from that. And that took a long time to recover from. It was sort of what's known as a coal gap, meaning there were no forests for about 5 million years, and a coral gap, which means there were no reefs in the oceans for a long time, and the oxygen levels in the atmosphere plummeted from something close to about 30% in the atmosphere compared to today's 21, possibly dropping down to 10%. So that's like being on Mount Everest, basically, at seafloor in terms of the oxygen density. As for the big dying, that's more complicated because it was such a bad environment for such a long time that was caused by these various factors, and we can see in the fossil record that there's the climate seemed to just fluctuate wildly for a good 5 million years after the mass extinction. So species that survived that initial dying still had to weather all these big changes that came afterwards, and it seems like a lot of the ones that survived were generalists. So we say today, if there's another catastrophe, it'll be the rats and the seagulls and the cockroaches that will survive. And they're they are quite good generalists. They can survive on just about anything. They're not specialized to any particular food, and they have rapid breeding cycles as well, which helps. So things like, say, an elephant that has a long breeding cycle, they might not survive so well, and only few offspring. And that seems to be the pattern back then as well. But there are other groups that seem to have weathered previous environmental changes that were knocked out.
Some organisms, such as the seafloor scavenging trilobites, survived numerous extinction events.
One of the most successful organisms in the sea were the trilobites, which were a type of arthropod. They were successful for several hundred million years. They evolved in the latest Precambrian, as far as we know, so we're talking about 550 or so million years ago, but they were extremely successful in the sea for various reasons. They also replaced several organisms that were really diverse, such as the so-called cup animals or archaeocyathrids, okay, which disturbed their habitats, and basically there was an arms race at this time.
So probably trilobites are in the top 3 groups that people know about when you talk about extinct things, just after the dinosaurs and the ammonites. They certainly were one of the very first groups that were quite dominant in the oceans, thousands of species right early on. Some of the very best eyesight with their compound eyes and a lens made out of a crystal of calcite, quite amazing, the only animal to ever do that. But they had weathered many different events, including, I assume, various different apex predators coming in from initially large nautiloids and then to the sea scorpions and then the armor-plated fish, and they seem to weather all of those with all these defenses, very spiny. But at the end, Devonian extinction events, they were heavily impacted, and almost none of them made it through except for one small group that sort of still struggled on until finally getting wiped out in the Permian. So they were almost all bottom dwelling on the ocean floor, really reliant on the sea floor. So you have the legs, you can sometimes see their tracks where they shuffled up the sediment and they ate the animals and other creatures that lived in the sediment. So if the seafloors were really starting to die and nothing sort of lived there, their whole food chain collapsed. So that, I'm assuming, is a major reason why they just couldn't quite make it through. They were heavily reliant on the seafloors being full of oxygen and full of life. It's quite sad because they're very cool animals. I mean, such a diversity and beautiful shapes.
One adaptable organism survived the Great Dying. Lystrosaurus went on to become the ancestor of dinosaurs and mammals alike, including humans.
So during the Permian in Pangaea, we know from the fossil record that there were high diversities of tetrapods, so 4-legged organisms like this guy here, which is called Lystrosaurus. For some reason, it had attributes that enabled it to cross this boundary relatively unscathed. So we know by looking at the skeleton, it probably did scavenge. It had a barrel chest in terms of air capacity as well. We know that the air was probably fairly thin. It was basically life under a green sky, very different from today because of the hydrogen sulfide gas. Very few other organisms persisted across this boundary. And of course, these were very important tetrapods because they evolved eventually into mammals, okay, including us. In terms of recovery, we estimate that it took about 100 million years for the ecosystems to recover after that mass extinction.
And then not too long after, I guess, a few tens of millions of years later, the end Triassic extinction occurred. It's possibly one of the most mysterious ones because I think there's fewer causes that have been identified for it, but it might again be big volcanic eruptions that caused big climate changes to occur massively.
Volcanism can have amazing impacts on climate and the environment. in several different ways. So first of all, if you have a big volcanic eruption, there's lots of dirt and dust and chemicals that get added to the atmosphere. One part of those are sulfide oxides, or maybe even hydrogen sulfides. And these can, first of all, form sulfide aerosols. These are really tiny particles that actually get into the really high atmosphere, and they can stay there for a long time. And by doing so, they will shield the atmosphere. It's like a blanket. So incoming solar radiation actually doesn't get quite through, and it becomes cold for a few days, months, maybe even years if it's a big eruption, and it becomes darker. If it's a really big eruption, it might even become so dark that photosynthesis becomes a problem.
Well, a lot of people think that the Triassic was pretty much a stressed environment throughout, largely due to the oxygen levels in the atmosphere remaining really low. So the oxygen levels in the Carboniferous to Permian, it's the big ice age there, had gone up to 32%, which is massive, like compared to 21% today. And largely due to the big growth in terrestrial forests that had evolved, and it allowed all sorts of things to evolve, giant insects. Towards the late Permian, even before the last extinction, oxygen levels really started dropping, and indications are that in the early Triassic, oxygen levels stayed close to 10 or 12%, which is half of what we have today. It's really quite extremely low. And it seems that they didn't really get up to closer to modern levels again until into the Jurassic, after the mass extinction at the end of the Triassic. But the interesting thing about it is that it probably encouraged some groups to evolve really efficient breathing. So if you think about the birds today, they have circular breathing. They don't really have to breathe in and out as much as they just they have lots of air pockets to really get the oxygen out. And that might be a legacy of the early dinosaur ancestors evolving in the Triassic to deal with these low oxygen levels. So that stressed environment had some unintended consequences later, which is why we see such success in the birds today, able to fly, which is high oxygen demand. After that, we have the big golden age of the dinosaurs that lasted for a long time until it was brought to the end by the most famous, popularly famous extinction, the dinosaur extinction at the end of the Cretaceous.
In fact, we now can date it to about 66.03 million years ago.
Famously, there was a big asteroid impact, probably the biggest asteroid impact in the last 500 million years.
So we're talking upwards of maybe even 1 trillion tons of rock just hurling through space, heading towards our Earth. And when it did actually reach our Earth, okay, it would have gone through the atmosphere within a fraction of a second, and it hit the Earth, created a hole that was probably about 30 kilometers deep, and we know about 180 to 200 kilometers wide.
So that alone is pretty bad. But there was also indication that there was a lot of greenhouse gases being emitted by these big volcanic eruptions, continent-wise eruptions in India that caused greenhouse spikes. And we can see that in animal populations that were pretty stressed already before the asteroid hit.
Any organism even close to it would have been basically incinerated from the fireball. Okay, so this again had this effect where it affected the base of the food chain because there was a dust cloud that enveloped the Earth. So it affected plants at the base of the food chain, and again we had this propagating effect all the way up through to the apex predators.
So the asteroid might have just been the last bad news for all of life, and it caused the non-avian dinosaurs to die out, but many other groups went as well at the same time.
So in our extinction story, it's really important to differentiate between background extinction and mass extinction. So when we actually look at background extinction rates, we can compare the modern to the fossil record. So we can actually delve into the geologic past by looking at organisms. And what we see, which is really important, is that, for example, if we look at mammal fossils, probably one mammal species per 1,000 years became extinct. So that's background extinction. If we look at the present day, we estimate that in relative to background extinction rates, the extinction rate today is something on the order of about 1,000 times, okay, what it is if we look at the fossil record.
Coming from a background of geology and looking into deep time, it's been quite well established that there is a clear, solid link between carbon levels, especially carbon dioxide levels in the atmosphere, and climate. Now, it's not always the carbon dioxide that causes the climate change to start with, but it's either the first thing that the change in carbon dioxide up or down is very closely associated with massive climate change. So sometimes the carbon dioxide changes ahead of time, so things like massive volcanism can cause warming. In some cases, like the Ordovician extinction, big mountain building, that weathering actually draws carbon dioxide out of the atmosphere, and that causes the carbon dioxide to plunge, which is what probably happened there, causing an ice age. At other times, it can be other causes, like the Earth's orbit can change its shape. It regularly does that in a predictable way. And then those changes from the sun's radiation causes a start in shift towards warmer or colder, but then that initiates sort of a feedback with the carbon dioxide. So the warmer it gets, often the carbon dioxide goes along, starts going up as well, which causes more warming, which causes more carbon dioxide. So carbon dioxide either initiates the warming or cooling, or it exacerbates the change. And the quicker it changes, the more rapidly the climate changes. And rapid climate change often leads to species not being able to adapt quick enough. And if the environments shift too fast for specialized species, they die out. And if that goes above what we call background extinction rates, we start seeing sort of the clear markers of mass extinctions. And there is the thought that at the moment the change is exceeding the rate at which species can sort of adapt. And it's not like with all the other mass extinctions, it's probably more a perfect storm of conditions, not just one like climate change or an asteroid, but a host of things. So we have not just climate change induced by humans at the moment, but we have deforestation or urban sprawls or habitat fragmentation, things like that, that are stopping species from adapting at a fast enough rate. So it's worrying to see where we're heading, knowing what's happened in the past.
It's really important that we actually understand these species and the effect that we're having with all this deforestation and other things that are happening around the planet, which is also affecting climate. Because another factor which affects species as well is, in fact, some groups of organisms are very controlled by temperature, and even the slightest increase in temperature can affect their distribution and actually make their populations dwindle through time. So there are various important factors, and these factors that control species through time relate to ecosystem energy supply. They relate to climatic events as well. So various aspects of climate, which are quite diverse when we talk about them. It could actually mean about where they live. To live on a seafloor in terms of bathymetry, there are depth constraints as well. With sea level rise and fall, that really affects them as well. So there's a huge number of parameters that affect a species through time and space, which are important to consider. And with so many species becoming extinct, we know that there's a massive problem in the environment.
Yeah, the ecosystems, particularly the rainforests in South America and the Amazon or across Indonesia, have been severely affected, not just by the changes in carbon dioxide, but initially by clearing And we also have our own very special rainforests that are extremely diverse up in the north of Queensland, and also an extremely diverse flora called the fynbos in both Africa and southwestern Western Australia. So these are extremely diverse biomes, and they're already showing significant extinctions as a result of both clearing and changes in the carbon dioxide levels that we've seen, which have been significantly greater in the last 50 years.
One of the groups that always gets raised as, well, how did they survive but the others didn't, is things like crocodiles and alligators. They've been around for longer than the dinosaurs and they're still around. And the recent massive freeze in Florida brought up some interesting images of crocodiles or alligators there basically poking their snouts through the ice and getting frozen in and going into a hibernation state. And so if you think about in this case, the mass extinction at the end of the dinosaur age, the Cretaceous, where there was probably almost a nuclear winter from the impact, that was probably a perfect way for them to survive that, where there was no food around for many years. So they had some ability to just weather it, whereas maybe some more active species like the sort of warm-blooded early birds, a lot of the dinosaurs that needed a lot of food, the big ones, they just couldn't weather it out for all those years.
If we pay attention to it, one other event provides a lesson in carbon dioxide absorption in the oceans: the Paleocene-Eocene thermal maximum.
The Paleocene-Eocene thermal maximum, which is a mouthful, we usually call it PETM, was a very abrupt, short warming event that happened about 55 million years ago. Atmospheric temperatures rose by 5 to 8 degrees. And what is interesting is that it's actually one of the biggest mass extinctions in the deep ocean. And that's unusual because usually living conditions in the deep ocean are quite constant, and we much more rarely see big mass extinctions there. So what we know is that this event was caused by a massive release of carbon into the atmosphere. There's still some controversy about where this carbon came from. It might have been enhanced volcanism, it might have been methane hydrates. But certainly this release happened fast on a geological timescale. We now pretty much think that this release happened at a much slower rate than what we see today, about at least 10 times, if not 100 times slower. And that has interesting implications, because if you add CO2 into the atmosphere, the CO2 will be absorbed by the oceans. And when the ocean absorbs this carbon dioxide, actually carbonate ions get depleted in the ocean. And that's bad news for any organism that lives in the ocean that builds shells out of calcite or aragonite, because they need these carbonate ions to actually build their shells.
Calcification rates, the way that the animals build up their shells with calcium carbonate, has dropped. There are things that are becoming thinner in their shells, which makes them more susceptible to other stresses, and that's just an additional problem for them. So climate change by itself isn't the whole story. The acidification is a big
due to two different physical mechanisms. One is, of course, melting ice caps, and we see this happening right now. Greenland is melting. Antarctica is starting to melt more than we actually initially thought. So there's certainly some tipping points there, because once an ice sheet starts to melt, it will continue to melt due to other feedback set. So when an ice cap starts to melt, it becomes less high. The lower it gets, the warmer it gets. You know, when you go up a mountain, the higher you get, the colder it gets. So just due to this change in height, it will start to melt faster. Also, the surface will become maybe a little bit darker because there's not much more snow accumulation. There will be more dust and other things that actually go on the surface. And especially regions where it starts to melt completely, what was white before will be replaced by rock or by whatever is underneath. These colors are much darker. They will absorb more incoming solar radiation and will become warmer. So there's several positive feedbacks that kick in once an ice sheet starts to melt. If we start to warm up our oceans, the water in the ocean will expand. And due to this expansion, we will experience sea level rise.
Oh, listen, people have been doing models for the last 20 years on, changes to the environment that are ongoing at the moment. And every time they produce a model, they have to revise it because the natural system is going faster than they modeled. So the Arctic ice, for example, that's down to about a third of its size. That was only 20 years ago. And so these systems are changing incredibly quickly. The danger is that we have this enormous system called the ocean that absorbs a huge amount of energy because it's so big. But once that reaches that tipping point and we start melting the ice and temperatures start to rise faster than they are now, which we know will happen, all the models show that, then we're in uncharted territory. And those changes are very hard to adapt to.
For humans, I think we are very vulnerable right now. There's lots of humans on this earth, and we all depend on a few cereal belts, a few regions that produce most of our food. We depend on water. With changing climate, precipitation patterns will change. Temperature will, of course, change. Will these structures we have been putting into place over the last 20 years, will they still work? Will they be able to actually support all of us? I think that's highly questionable. On top of that, of course, we will see sea level rise. All these things will also happen if we stop emitting right now. But it will be maybe easier to deal with the consequences the sooner we stop. It might just be too late at some point very soon.
I think as humans, we've been able to do some amazing things with our own needs, like the crops we've been able to genetically modify to try to increase the amount of food resources that we have, to try to provide for these, huge increases in population in humans. But I think the question is, can we keep pace with the increases in carbon dioxide in the atmosphere and the changes to our climate? So we're seeing much greater extremes of climate and much greater extremes of very hot, dry events, particularly here in Australia. So it's a question of whether we're able to keep pace with those changes, even with such technologies as genetic modification.
So the Anthropocene is now a word that's very widely used. It's still not formally defined. There are people who are working on it. In fact, there are people here in our building, in our school, who are working on that. They've just had a paper about an actual marker for the start of a new geological era, the first sort of nuclear bomb spike that is recorded in tree rings, for example. But yes, I think there are many arguments that suggests we are entering a new geological era. So there's two things to think about here. One is, are we entering a new climate state? And I think most people would agree, definitely yes. But in terms of geology, so you have to think about what's preserved in the rock record, the geological record. And absolutely, there too, we are into there is actually a new rock forming now that's made up of solidified plastic. And that will not break down over time. But that is a new rock type that's been found offshore of Hawaii and various other places. And there are new chemical elements because of these nuclear explosions preserved in the sedimentary record of the sea. So geologically, yes. And because of the increase in the amount of rainfall, the amount of temperature, the rate of erosion is faster than we've had before. So there are thicker sequences of sediments in the deep sea that are accreting. So that is a recognizable change that we could see in the geological record. So aside from the pedantic niceties of saying geology, there are physical changes recorded by Earth in this sort of rock record that are suggesting we're into a whole new period.
Changes in our oceans, such as releasing toxins and plastics, can also have dire consequences for the diversity that we see in the ecosystems today.
Again, I'm not a biologist, but in my opinion, yes, I think we're in a period of mass extinctions. It's not the normal background extinction rate, the fact that every one of us has seen many species going extinct during our lifetimes. That really shouldn't be the case. So yes, I would say so.
So are we entering the sixth great extinction event? Many would say we're already in it. We haven't entered. We are not entering. We are in. If you look at the amount of species that have become extinct since really the dodo and the passenger pigeon in the States from the late 1800s, since then the rate of extinction of species is also one of these exponential curves.
I think that the evidence points to a sixth mass extinction. If we were able to time travel into the future and look back at the fossil evidence from today, we would see the last 10,000 years in a very short space of time. So we would see that the megafauna that were like the saber-toothed tigers and the giant bison across America, or in Australia we would see the megafauna like our marsupial lions and giant kangaroos and giant wombats would all become extinct in a very short space of time, as well as the increase that we see in extinction of species today. So I think that we have already entered this sixth mass extinction in the Anthropocene.
And, you know, the danger is that there are so many species that are uniquely primed for very specific purposes. When that purpose changes, say the size of a flower, the growth up a horizon of a mountain chain, where they live, you know, there are birds that only live within 400 feet of a particular mountain. They're being forced up the mountain, and eventually they're just going to have to go into the sky. Their habitats are disappearing as we speak because they're so fine-tuned for life. So as the habitats change, whether for good or bad, you know, climate change brings more growth in some areas, less growth, more dry in others, but that change means that species will go extinct.
A major issue that we as humans face today is species loss. And this is occurring through deforestation, building. This is happening all around the planet. And what's happening is that species ranges are becoming contracted, dissected, and they cannot move between one place to another. So this will affect the gene pool as well and genetic diversity, because there's really a minimum number of in a population to sustain that species through time and also in space.
Now, under natural geological Earth processes, nature would adapt and new species would arise to fill those gaps. But because the change is so fast now, nature cannot adapt at that speed. And that's the danger. We're left with a very few successful species that can adapt to change, and we're one of them. We can adapt. We live everywhere on the planet, so for us it's all fine. It's not fine, but we can adapt to that change. But there's so many species that can't, and they are disappearing now.
But my personal concern is really the change, above all, is the change in chemistry in the ocean and also the change in water availability. and what is going to happen to our ecosystems, because our ecosystems are already under stress due to climate change. But on top of that, we add stress to overfishing, overhunting, habitat fragmentation, habitat loss. I think there's only that much that these ecosystems can take. And in a way, we are part of an ecosystem. We need an ecosystem to live ourselves. We need to eat, we need to drink.
One of the things about geology is about rocks, about processes that, are preserved in the rock record, is that they compress time. So, where the dinosaurs went extinct, that was probably over 1 million years, but we can see that as a layer about that thick. So if you think about all the change that's happening now, all the plastic and pollution that's going into the environment, as that goes into the deep sea and it gets buried and buried and buried, it gets compressed in these very thin layers. So that will have this enormous geochemical spike of all these manufactured components that will be preserved under a very thin horizon. So millions of years from now, if I was able to travel forward into the future and then come back and look and say, what has gone on here? Because it's so compressed, so much change is going on at that one specific interval. This is a massive catastrophe that would be recorded all around the globe. So you get these runaway effects. And so runaway effects, and we're already seeing it, right? So more than half or even 3/4 of the world's population live in low-lying areas at fertile river deltas at the coast of the oceans. All the big cities in the world are where there's a nice view over the ocean, right? So now, if the ocean rises 120 meters, OMG, the deltas, the fertile deltas, where all the rice is grown, where all the grain, all these things are grown, they disappear. And so as those oceans flood, and some people have suggested this can happen on the order of 100 years, more than half of our food source is gone. Fishery stocks are being depleted around the world. And those are primary food stocks. Primary food is the key. If we don't have the primary food stocks and fresh water, the basics of life, it's not about whether you got a mobile phone or a computer, it's about whether you've got food and water. And so if we don't have food and water, our population will totally crash. But less human pressure allows nature to expand. There's a lovely example in Chernobyl, where the nuclear disaster happened in Russia. The forests, the whole city was abandoned, and forests have come back. Wolves have come back for the first time in generations. There's a viable population with moose. There's a whole ecosystem and chain that is set up. So we know that nature can come back. It's allowing it the space and the time to be itself.
I think that the world we know today won't necessarily exist for too much longer if we keep increasing our carbon dioxide. But I think it's more the humans that we need to worry about. We're the ones who evolved in these much cooler times, much lower carbon dioxide in the atmosphere times, and it's whether we can help the species that we require and keep our diversity on Earth into the future and make our own species survive.
So yeah, we've got carbon dioxide rising, we're changing, we have to mitigate how we build, where we build, we're planning about the future, building back on higher ground, transporting water, using wave energy, all these kind of ideas about adapting to the new. If you then throw something on top of that adaptation, for many, including our species, that could be too much. Yellowstone going off would be a cataclysmic disaster. Yellowstone is known to have covered 1/3 of the US in death-causing ash and gases, not to mention all the cloud effects and global changes in temperature.
Cut emissions now as fast as possible. I think climate change is actually the biggest threat humanity has ever faced. And it's an interesting threat because it's something we have to do something all together. In terms of pollution, for example, if you have bad pollution in one country, then one country can decide that's not good for us and they change their policies and then it will be fixed. In this case, a whole human species has actually to cut emissions. The faster, the better.